That's probably true.
Culture difference.
Yeah, it's because we think it's going to be okay.
Yeah. Like,
Interesting.
yeah,
Oh.
I want to write a thesis about the culture
This is, yep.
difference.
This is the cultural thing. Oh.
What do you guys all think of Mohammed's lecture? It's confusing, right? It's like the likelihood principle. So maybe we'll just leave it in the confusing box, and if you guys want to have a discussion with me about it, you can. So just know what the statement is. Also note that there's no proof or disproof. Maybe likelihoods are a good idea. I kind of like Danielle's point. It's like it kind of keeps you in bounds if you follow the likelihood principle. What's a violation? Apparently everything. So it's okay. That's also okay. Welcome back, everybody. We're going to jump into something a bit more practical. So I'm not sure you can do anything with the likelihood principle, but you can certainly do things with likelihood functions. So I use them. You're not obligated. So saying that, if you know what your model is and you know your modeling assumptions, I'll probably ask you, why don't you use the likelihood function? So if you don't, you're about to get clobbered. So by who? By me. So saying that, I'm not going to jump out of the bushes and like rework your analysis. If you're in the ballpark and you say reasonable things, you can justify and explain what you mean. What are you trying to guarantee, so on and so forth. I'm going to think you're a good statistician. If you sit around and you argue the likelihood principle all day until you're blue in the face with people and you don't do any analyses, I'm going to think you're not a good statistician. So you might be a philosopher though. And ultimately we all are. So you know, when I watched Mohammed's lecture, he was saying things like, it's interesting, you know, and it is interesting. So that's a personal thing. I'm also interested by things all the time about what can I do with them all. There's more practicalities in mind that we have to think about. I want to jump into one of them, the Eem algorithm. So the Eem algorithm is aptly named. Let's try these. It's aptly named. Obviously, a statistician named this thing, because they tell you exactly what it stands for. This is that. I have typos. So this is expectation. And this is maximization. So not a very good name, but it tells you exactly what it is. So maybe in some sense it's a good name for an algorithm. It just doesn't sound very cool. That's what lets you know whether or not a statistician or a computer scientist named this thing. And so I'll change some names throughout this and tell you what other people call certain functions. I'll tell you what I call certain functions, the names that I use. And it's not meant to be contentious. I will say, I think this employs Bayes. Is it a Bayesian algorithm and does it need to be used in a Bayesian context? Absolutely not. I think that there is a hook in this algorithm that is Bayesian, and there's no way to reconcile that in my mind. I'll tell you what people are talking about and where the argument arises, saying that if we don't argue about it, it's still a good algorithm. So let me tell you real quickly what the goal is. So goal, same thing, learn data. So some parameters, model parameters. So I'll say these are the parameters of interest. That's been the goal all along. Learn parameters of interest. Let me be a little bit more specific. This algorithm always concerns something that's missing from you. Now, I don't want to be too general. Last time I spent 10 minutes quibbling over what was missing, what could be missing. I'll just give you an example up front. But let's just write down what we're dealing with. We have some function, and it's going to be a function of parameters of interest. And there's always going to be something missing in this algorithm. I'm going to write it down the side. So this is missing. And then there's going to be some data floating around. So you can think about this function rather generally. I can think about this maybe as a likelihood function. So it could be a likelihood. Could be a posterior distribution. Could be anything where I'm just treating theta and psi as some sort of random argument. It's going to be conditioned on your data. Oftentimes in the context of EM, they'll call this the complete likelihood function. So maybe since we're statisticians, or at least pretending to be in this class temporarily for at least 50 minutes, maybe you think of this as a likelihood function. So that's the way I usually employ this. I'm usually doing this on a likelihood function. I have some likelihood function. What I might want to do is maximize this parameter right here. This is missing from us. The Eem algorithm is not just an algorithm, but it's also an inferential method. So it's going to do two things. It's going to maximize this parameter, and it's going to average over this parameter. So there's kind of a hybrid technique happening already. So I want to maximize theta, and I want to average out what's missing. So we're going to average this way. And then we're going to maximize this. So we're going to integrate over psi in the first place. The Eem algorithm is two steps. It's an expectation and it's a maximization. So when I average, I'm taking the expectation. And when I maximize, I'm looking for the maximum. So that's where the algorithm derives its name. So it's these two steps. And it iterates over these two things. I'm going to prove that this algorithm actually does what I say next time. We'll start with an example though. So EM solves this sort of thing right here. I'm going to say the averaging over f theta psi, given my data. I'm going to integrate over psi. So I'm going to average it away. You might have a problem with this already. So anybody have a problem with me doing this to a function?
Isn't psi missing?
What's that?
Isn't it because psi is missing?
Yeah, maybe. So psi's missing, whatever. Everything's missing from us. All the things we ever want to learn, we don't ever get to see. Otherwise, we would just know it.
Don't you need like to multiply by psi if you're doing an average?
Yeah, so multiply by a weighting on psi. So I kind of agree with Peter, like I'm taking an average right now. Don't I need to multiply by psi? I would say a weight on psi. Anybody else want to add to that? Why can't I just integrate over a likelihood function? This is not a random variable. So if I'm going to take an expectation, if you've been through probability class, and all of you have, that needs to be a random variable. And so if this were a posterior distribution, no problem. Go to town. I've already applied Bayes' theorem. That's what Peter's expressing to us is, can't be a likelihood for me to just integrate over it. You have no right to do so. So Fisher had an argument for this. He said, well, I automatically upgrade my likelihood functions, the parameters in them to random variables. That was his fiducial argument. So his fiducial argument was just go ahead and do it. The Bayesian says, oh, what you mean is you're going to apply Bayes' theorem, but your prior is uniform. So Fisher was kind of saying that. He didn't want to concede that that was Bayesian. So a lot of times when Bayesians see this sort of thing right here, where you're going to integrate over something, they think it's a random variable, we're all adhering to the rules of probability theory. And then some people say, no, you don't have to adhere to probability theory for a moment. And the Bayesian will say, well, you're being a Bayesian, but you haven't stated your prior. That's what Peter's saying. So maybe my prior is integrate over 1 or something like that. We're not going to quibble over it quite yet. When we get into the algorithm, and in an example, we'll quibble a little bit more. But when I used to see this and people would do integration over a variable, I would do the same thing that other Bayesians do and say, are you a Bayesian? And people would either go yes, or they would get angry. So it's okay. So that was the first lesson of the day, right? It's all right. So we'll say it's okay. I'm just going to call this a function of theta. And it has data in there. And so the Eem algorithm is going to solve for this. Theta hat is going to be the R maximum over theta of this function. So there's, I don't want to just take this super lightly. That the Eem algorithm is averaging out a parameter and then it's maximizing. So it's kind of this like, well, I'm looking at maybe an MLE, but over the average of psi. So when we do that average, I'm really thinking Bayes. So we'll see this a little bit more formally through an example. So maybe this is in some sense the MLE, but it's not exactly an MLE because I've averaged over psi. So we have a couple choices that we could do. If we were full-blown Bayesians, we would have constructed the posterior distributions over theta and come up with the distribution over it. And there is an MCMC technique for solving all these problems as well, and you can treat the whole thing as Bayes, or you could do what the Eem algorithm does and converge to some maximum over theta. We had another choice. We could have maximized over psi and theta simultaneously. So I'll just write that down. A different solution. Might be R maximum over theta and psi of f theta psi given data. I could have given you this. Theta hat, psi hat, and maximize over those two parameters. I would argue this is a better solution than that one. Somebody help me out. Why is that? Why would I maybe argue that that's a better solution? That's a better technique than this one. Well, it just has to deal with the properties of averages. I'm uncertain about something. There's a lot of values that psi could maybe be. So maybe I don't want to stick in the best one, but I want to smear it over its uncertainty and deal with all the uncertainty. So averaging does a nice thing. It makes sure your answers are good on average. So if you keep doing it over and over and over again, you tend to be good. So maximums sometimes miss the mark. So they're a little bit optimistic. So I would probably argue if that's the case, you probably want to come up with a full distribution of theta as well. and deal with its saying that this is a method that gives you a point estimator for theta. So if I wanted my best guess at theta, and somebody asked me for it, I'd probably say probably the maximum. How do I deal with this other thing, this nuisance parameter? Average of it. Maybe that's a good answer. So still, I would probably want to express uncertainty over theta as well eventually. But if I were just going to give you something, an answer, maybe theta half. Being the maximum is a good answer. But usually I think that parameters that you're uncertain about, average over those. So I like average instead of just here's some answer I consider the best, but in some context it might not be the best. A lot being said right there. So, but average over things you're uncertain about, I usually say to do that. I usually do that. Sometimes if people ask me for what's my best answer, maybe I'll give the maximum. So I think that they're dealing with a missing thing quite properly. So say, I don't like this because it doesn't deal with uncertainty in something. So it doesn't deal with uncertainties. About psi, what's missing. Okay. Any statistician is also going to quantify your uncertainty about whatever it is that they're giving you. So that's going to be the thing that distinguishes a statistician from somebody that does OR, operations research, you know, where they're basically dealing with maximum. So the field of optimized. So OR, they get that sometimes. So statisticians are a little bit different from OR people, that we don't quibble over how we did the maximum, and that's what OR people are always doing. They're like studying the algorithms to maximize. I like that stuff too. I do that all the time. But statisticians also will say not only what their best guess is, but also give you intervals for their best guesses and say these are all reasonable guesses. So somewhere in here. That's what distinguishes our two departments on campus. So everything OR does is interesting to us as statisticians. Everything we do as statisticians is interesting to OR. That's just culture. So totally fine, as long as we talk to each other. So OR people are going to give us our fast optimization algorithms. Statisticians are going to jump into the debate and say, well, what are other good answers as well? I like your answer, but you give me some other reasonable answers that are maybe not as good. Okay, so with that in mind, we're going to solve this problem. And the Eem algorithm solves it by these two different steps. And I'm not going to prove this very moment that the solution to that problem is this algorithm, but I'll prove it next time. So I think if I were a mathematician, I would prove first and then show you an example. Because I'm me and not a mathematician, I'm going to show you an example first, and then I'll prove. Again, culture. So, Eem algorithm. So it's not exactly the same, but the solution is the same. We'll study these two steps. Next time, we'll prove that this is the solution to this problem, but at least for right now, we're just going to work with an example and show what these two steps do. So this is the E step. Very boring. Call it the E step and the M step. Should have come up with better names. So I would say this is the light side, and this is the dark side. I love averaging. I think that's like brings light to our world. It deals with uncertainties and maximums are a bit too optimistic. Okay. Enough of my Star Wars antics. So there's a function that you form. And this is going to be the expectation. We're going to to change the problem a little bit. Log of whatever this function is, I'm usually thinking about it, is a likelihood function. And I need to tell you what the expectation is over. If you saw this, you should instantly go, what's theta t? I don't see it over on the right-hand side. So it's this thing. This is going to be integrate over psi. That's how I'm getting rid of psi, and I'm going to condition on theta t. Right here. And then I'm going to take theta t plus 1. It's going to be the R maximizer over theta of q theta. Given theta. So just to be more specific, this thing in a continuous context or discrete, I change my integral operator to a sum. This is going to be the integration of log f beta psi given data. And I'm integrating with respect to this function right here. This is going to be f psi given theta t. Now, I also want to be a little bit more specific in all of this. When I write down that I'm conditioning on data, I condition everywhere. Anywhere there's a function I condition on the data, it can. So sometimes you'll see this written, but I also always mean this, given the data. So I'm going to integrate with respect to what the data says. And then I'm going to integrate away psi. This is starting to feel pretty good to us. When I write down a function like this, Peter's happy because at least I follow a probability theory. If I'm going to integrate over a parameter, I better update it to a random measure. That's what Bayesians do. There's a lot of flexibility right here on how you do this. So in the context of missing data, let's just say I were actually studying a problem that I saw a spreadsheet of data. I had y's and I had x's. So I want to explain some y's given some x's. So basic regression setup. Missing is much more interesting than I'm making it sound. That it's like, oh, it's just missing. What somebody would do, a modeler would think about why is it missing. So there's three possibilities. Maybe something is missing completely at random, that they fill out their survey, fill out the responses that you're interested in measuring, they fill out all their covariates. So I write down, my name is Scott Lehman, I'm 46 years old, I grew up in California, I now live in Blacksburg, Virginia, my zip code is this, here's my bank account information, you can have it all. So, you know what we do. And we hope nobody takes all our stuff. So, and then I tell you also the response. So how do you feel about something? You know, the impact of global warming or something like that. I'm very angry. So when they're trying to measure, oh, it must be because I'm from California. I'm very angry. It's going to fall into the ocean. So if I went into that survey for all of you and I cut down your demographics and I cut down how you feel about global warming or whatever we call this now, climate change, whatever it is. So it's getting warmer on average. But maybe that's not a great name because people don't like averages. And I went through and I just scrubbed a few of the entries. So Stephen's stuff, I took out the fact that he's also from the west side of the United States. Doesn't want anybody to know that he's from the west. So, well, the east, they don't like that. So he takes that out. Don't want you to judge me. So he just, you know, so that's different from just erasing it at random. He did it for a reason. So maybe he did it from the context of climate change and says, I don't want you to know I'm from the west because I think you're gonna use that against me. So it had to do with the response, why Stephen decided to erase his zip code. Stephen's on the spot right now. So nobody's gonna come and get you. So Stephen's not. So he's not very big on climate change. So saying that, if he just erased something at random, that would be a different mechanism than erasing it because of the response that you're trying to gauge. And it might be different from if he erased a spot because of certain X's and not the response. So there's a bunch of different mechanisms in missing. There's missing completely at random. It's like you erase something just randomly. So maybe it's a computer glitch. There's missing because of the response, and then there's missing because of other covariance. So maybe somebody doesn't write something down because of another X. So in a missing data class, they would teach you all these mechanisms and try to teach you to model it. Why is it missing? I'm going to forego all of that in this lecture. And I'm going to give you a rather simple example. But this example is super useful. So in a missing data class, it would have you model this right there. There'd be a lot more conversation as to why things are missing, and they would add it in to their model. Okay, enough about that. So let's study mixture models. So I'll say finite mixture models. Finite mixture models. I'll say count K components. And this is the part of the class I'd like to supplement that's not in your book. So let's give you something fancy so that you can use this throughout your entire careers. So finite mixture model looks like this. X is going to be distributed. Well, I'll say this. Let's say I wrote down, let's make this really specific. I'll say normal mixture models. So X, if it were just a one component mixture model, I'd have X comes from some distribution that contains mu and sigma. Okay, so this is a very boring mixture model because there's only one component right here. So this thing right here is 1 over 2 pi square root 2 pi sigma e to the minus x minus mu squared sigma squared. There's a 1 in front there. So our old friend, the Gaussian, looks something like that, where this is going to be centered at mu sigma. That's probably the worst normal distribution I've ever drawn in my whole life. So let's make that look a little bit more convincing. So it comes down here, down there. So mu sigma. Okay, so this is a one component normal mixture model. Now I'm going to do something a little bit different. I'll not change too much of this. I'll put some i's right there, where I can go from 1 to n. So if I were sampling from this problem, it would be n samples from this. And if I collected those n samples and I drew a histogram, it would start to look like this curve. The more points I got in my histogram, it would smooth that thing out so it looked like this curve. And I'd be able to tell you what mu and sigma were. So now I'm going to do something just a little bit different. So I'm going to say, I'm going to have this additive mixture model. Additive meaning that there's a sum. K goes from 1 to cap K right here. And I'm going to add some little indices for this right here. So I'm going to change what this distribution is by adding that there's K different standard deviations, K different variances, and K different means. But I'm going to be really specific, and I'm going to add this indicator function as well that says xi comes from component K. So let me just write down in xi comes from component k. And k is going to have cat k different possibilities. So instead of just this curve right here, what I'm going to be dealing with is a whole bunch of these curves. So if k were equal to 3, example, cat k is equal to 3. What I'm sampling from is 3 different normal mixture models. Now I've drawn these to have 3 different heights. I haven't annotated that in my picture. We've also got some sigmas in here. Sigma 3, sigma 2, sigma 1. And so I'm not sampling from all of these things simultaneously. I'm sampling from one of them. How often do I sample from this one versus this one versus this one? It has to do with how much area is under this curve relative to the other ones. I need to add one more parameter into this model. I need to tell you the sampling frequency. So I'll say this is the sampling frequency. I often don't say it that way. I usually call this a mixture weight. So lots of different things we can call this. So pi k's, also known as mixture weights. So here's the idea. To sample from this model, what we're going to do is we're going to flip a 3-sided coin with probabilities being equal to these things right here. Since I'm calling these a probability, I need to tell you that the pi k's, sum k goes from 1 to cat k, are going to sum up to 1 because I'm thinking of these things as probability functions. These individual things are going to be elements between 0 and 1, so they're all positive. So I'm thinking of pi k's as a probability of sampling from the k component. So here's my algorithm for doing this. So to sample, from, I'll say this thing right here. There's 2 steps. One, I'm going to sample, I'm going to flip a 3-sided coin to declare which component I'm going to sample from. So I'm going to flip a 3-sided coin, and I'm going to get an index in our example that's going to be either 1, 2, or 3. So what's the name of that distribution that I'm sampling from?
The multinomial.
Multinomial. So it's the extension of the binomial. There's more cases than 2. So I'm going to just sample from a multinomial. So I'm going to say CI. This is my component label. Component. Number. In our example, it's going to be a 1, 2, or 3. It doesn't really matter. They're not ordered in any specific way. It could be red, blue, green, or something like that. They're just classes. So I'm going to say this comes from a multinomial. And multinomials have parameters. Those parameters are the probabilities, pi 1 out to pi cat k. element of 1 cap k. In our picture, it's going to be a 1, 2, or a 3. I'm going to explain this a little bit more generally with cap k being our finite number of mixture components. After I sample this, then I'm going to sample from the corresponding normal. And so then I'm going to take my xi, let me write it down with purple. Xi is going to come from a normal right in my argument x. And then I'm going to have a mu and a sigma in here. Which mu in the sigma? I'm going to write down that this is going to be ci right here. So I flip a coin to select which component I'm going to sample from. And then once I have whichever component, let's say I flip the coin, it lands on 2, then I'm going to take a normal draw with this component.
In the mixture model that you wrote xi is distributed, and then you have an xi on the right side as well.
Yeah, so I'm going to just do this for I, who's going to go. So I don't have my xi right here. This is a dummy argument.
No, on that one. On the other board. The right board.
This one.
Yeah.
Yeah. So I wrote it down a little bit different both times, didn't I?
Yeah. Okay.
I guess that's better. Just a dummy argument, that's the whole space of x's right here. And then this is going to be my specific realization. So sometimes I miss the notation. So let's keep it straight. So what I'm going to do is I'm just going to repeat this thing. 4 I goes from 1 to cap n. So I'm just going to do this over and over again. So I flip a multinomial coin, and then I sample from its distribution. You should note that I could do this with any arbitrary functions. They don't all have to be Gaussians. It's convenient sometimes to make them all the same distributions. In my research, oftentimes I change the distribution. Normals are nice, and I'll say that this k-component finite mixture model is nice. If you're trying to model something that's smooth, I can model that, even if it has lots of bumps in it, or if it's super skewed, by using a finite mixture model. So I can approximate any smooth distribution using this. If it's smooth but super wiggly, I'll probably need a lot of components. If it's smooth and symmetric and not too wiggly, I'll probably need just a few components. So this is a general modeling tool. I do it all the time. If you're thinking about things like personalized medicine, so maybe each one of these different groups are a subpopulation and how you might react to certain medicines. So COVID, we've been studying, we've been hearing a lot about. It seems like age groups respond differently to, and that kind of makes sense. So younger people tend to be healthier. Kind of a tragedy, but it's just true. So maybe these are different subpopulations in how they might react to some disease or something like that. So I kind of like this. So instead of talking about things on average, I can start breaking things down and talking about subgroups, and then talking about the average behavior of the subgroups. So I use this tool all the time, mixture models. Okay, so how do we sample from a mixture model? I flip a coin, and then I sample from its component. So pretty straightforward stuff. We've done this early in class. So when we were studying a bootstrap, when we were studying averages, stuff like that, we used a multi-component normal model. So you can back up in class and see that we played around with this sort of model already. Okay. So our goal for this example is to learn the unknown parameters. So our goal going to be given. And I'll make this problem really easy first. So this is the easy problem. Given xi's, x1 to xn, and this is the part that makes it easy, my component labels, C1 to Cn, if I got to see these, this problem is actually really simple. So all of these correspond to each other. There's an x2 in here, and there's a c2 in here. So the ci's in the xi's come in pairs. They're paired together. And if I showed you both of them, if I told you what the xi was, and I told you what the ci was, everything's super simple. So our goal, given this and this, we want to learn our parameters. What are the parameters in this model? So I've got the mu's, so I'll say mu k's. This will be my notation for mu1 to mu k. What else? Sigmas. Yeah. Statisticians are always like, tell me more about sigma. So I want all my sigmas. What else?
Pi.
Pi's. I also need to learn the pi's. So I need all of these things right here. So I'll say this is a set, this is a set, this is a set. So I need to learn all those parameters. So I need to know how often I'm in each one of the subclasses, and I need to know their underlying parameters. How would I do this? If you were to learn this, what would you do? Say somebody comes into you, says, hey, you're a great statistician, you're getting a degree in statistics. I've got C's and I've got X's. Please help me estimate what the mu's, sigmas, and pi's are. What would you do? Let's say they made your life even harder and didn't even make you think. And they said, well, I want your best guess. And then they say, okay, since you look confused, how about the MLE? No, choose for you which technique. Oh, thank you so much. Now I don't have to make any decisions. I'll do a calculation for you. That's not what we do as statisticians. We also tell them why we're going to use a particular technique. But let's say they say, you compute the MLE, I can't do it. How would you do it? So my mu k would be equal to what? I'll throw a hat on there to tell you that it's an estimator.
Just like x bar?
Look at x bar. Which x bar?
K bar.
Yeah. So I can't just take x bar from this thing, not all of the x's, but I'll just sample the x's that come from component k. So I'll write down, this is going to be the x bar right here, divided by n. That's our typical thing. But we have to be a little bit careful that I only want to use the xi's that are an element of component k in the first place. So these are going to be the x's from component k. How many of those are there going to be? I'm going to give you some notation. I'm going to call it nk. And then I'm going to divide by nk. So this is x bar from just the points that came from each individual thing. So if I told you, for instance, these are the data points that came from component 2, I drew a histogram of them. and I told you specifically which points came from component 2, I would just average those. So I'd take all of the labels that were 2, and I would average those. How would I compute the variance? Similar sort of thing. So sigma k, and I'll write down squared. Make sure I put my hat on here to tell you that it's not the truth, but it's my guess. And this is going to look like sum of the xi's minus my mu k hat that I just computed. And I might divide by nk right here. There might be a minus 1, depending on if you like biasing this or whatever. So I'll just put that as a question mark. Both are decent estimators. If n is relatively large, both estimators have merit. So this is going to be my xi's for an element of ck, nk right here. And this is squared. So maybe that's my best guess. How would I estimate pi k? What would you do? I would just see how many times, if I were looking at component 2, I would look at how many times component 2 came up relative to everything else. So I'd use maybe a frequency-based estimator. So this would be the frequency of component k. How would I do that? I just look at sum of the xi's for an element of component k. I'd sum this over I goes from 1 to n, where n is my data size, and I divide by n. So this is just a sum of 1s and 0s right here, and it would be the frequency of everything. So kind of your commonsensical MLE. So this is maybe what I would do. If I were a full-blown Bayesian, I might regularize these a little bit and add a penalty to it, but asymptotically, I would converge to these estimates. I think that's what most people do. Please.
Isn't that just nk over n?
What's that?
Is that quantity just nk over n?
Yeah,
The
this is
nk we use.
Yeah, absolutely. That's a good way to write that down. So, NK over it. I like that. Okay, Eem's going to do something different. So it's going to follow these 2 steps. And so step 1 of all of this is to evaluate this thing. So we have to back up a little bit. We need to write down what the likelihood is. And that's what I want us to take a break and think about for a second, is what is the likelihood function? So my likelihood of theta given, and I'm going to write this down. This is going to be missing stuff with my data. Okay. In this context, this problem, nothing's missing if I give you everything. So here's what I'm going to do. I'm going to remove this from you. You don't actually get to see this. So usually you just get the xi's, and you see a histogram representation of this distribution. So what I get to see is this. So this is what we observe. These are my xi's, x's. And so if I showed you this data point right here, and I asked you which component do you think it came from, you'd be able to answer pretty easily. I think it's the one on the right. But if I gave you a point right in here, you wouldn't know which component it came from. So I often tell people the tail behavior is the most important thing in a model. Obviously, the where it's centered is probably the most important thing. But since we all know that, I usually move on to the thing we don't know, and that's tail behavior. We don't know where these sort of data points come from. So what you could do in this problem, here's one technique, is I could draw the histogram and I can go through with my finger and label everything. And that doesn't seem very statistically like justified. You know, in a high dimensional space, it definitely is not something you can do. In this one dimensional example, maybe you can label it. So EM is going to do labeling for us as we run through the algorithm. And that's what the E step is going to be doing, is it's ultimately going to be labeling everything. What we need to do when we observe all of this is we need to write down the likelihood function. Our missing stuff in this problem is going to be this. These are going to be the size. So these are going to be my thetas. We've already got that. These are going to be my size, and this right here is going to be my data. So in the context of EM, the missing thing to us in a mixture model are the labels. That at least gives you a starting point for thinking about this. What do you mean by missing? It kind of depends. So in a mixture model, something is missing from it. There's a Wikipedia write-up on this exact problem. So what I would do is I would encourage you to go study the Wikipedia page on Eem Algorithm for normal mixture models. They're going to provide you a solution, and I'm going to talk about that solution in class next time. What I'm going to ask somebody to do, and I'm going to ask at random somebody to write down the likelihood function, the complete likelihood. So, and hopefully somebody can do it. So hopefully on Monday morning when I say, hey, who's ready to write down the likelihood function, you're all like, let me do it. I'll give you a bonus for it. Whoever's the most eager and wants to write down the likelihood function first, I will give one homework point. It's not much. Somebody's something. So let's come back next time. Write down the likelihood function for this. Then let's take a logarithm of that likelihood function and take the expectation. When we take the expectation, we're going to be making the Bayesian hook in all of this. We're going to be upgrading things to a range of everything. So next time we'll come back, write down the likelihood function for this model. We'll write down exactly what the Eem algorithm is, and then we'll prove that the Eem algorithm actually works. So that's going to be our outcome. That's it for now, you guys. Thanks so much, and have a great weekend.